Hi, this is Barrett Givens from Cal Poly Pomona, and I'm here to talk to you today about modular arithmetic. In this particular screencast, I'm not going to talk to you a lot about the theory of congruences or modular arithmetic. I'm more just going to demonstrate some examples and talk about how to quickly be able to do computation, and in particular how to reduce modulo n. So to start off, of course, though, we have to start off by knowing the definition of the terms we're talking about. So the definition of A is congruent to B mod n is that n divides B minus A. I can rewrite that as B minus A is equal to n times an integer k, and by adding A to both sides I can rewrite that as B is nk plus A. So these are all different ways to think of A is congruent to B mod n. I should mention here that n has to be greater than or equal to 2 in this definition, and also that I didn't write it down, but a, b, n, k, and every other variable I use in this screencast must be an integer. So let's look at an example. Let's consider n equal 5. By the definition, a is congruent to b mod 5 if and only if 5 divides b minus a. So as an example, 27 is congruent to 12 mod 5. And that's because when I subtract 12 minus 27, the answer is negative 15, which is a multiple of 5. I also could have done 27 minus 12, because that will just be positive 15, which is also a multiple of 5. So in general, even though the definition says b minus a, you could also do a minus b. The only difference it will make is the sign, which won't affect whether or not it's actually a multiple of n. Here's another example. Negative 33 is congruent to 2 mod 5, because when I subtract, negative 33 minus 2 is negative 35, which is a multiple of 5. Now, one way to think about congruences is to think about a number line. So I'm going to take this number line here, and I'm going to mark off all of the multiples of 5. Now, the thing didn't, well, not all of them, some of them. Imagine it keeps going in both directions. Now, the thing about multiples of 5 is that if you take any two multiples of 5, then the distance apart they are is also a multiple of 5, right? So, for example, from negative 5 to positive 10, those are 15 units apart. So every single one of the numbers on this number line, every single one of these multiples of 5, they're all congruent mod 5. Now I could shift all of these numbers up by 1 and get a new set of numbers that are all congruent to each other. So shifting them up by 1, I get 1, 6, 11, and negative 4. And those numbers are all congruent to each other mod 5. Again, shifting up by 1, 2, 7, 12, and negative 3 are all congruent mod 5. 3, 8, 13, and negative 2 are all congruent mod 5. And 4, 9, and negative 1 are all congruent mod 5. Now what I want to do is I'm going to group together the numbers that are congruent mod 5, so the numbers that are color-coded there. So first I have all of the ones that were congruent to 0, 0, 5, 10, 15. Then the purple ones, 1, 6, 11. The white ones, 2, 7, 12. All of the red ones, and all of the blue ones. And by looking at the number line, I hope that you can convince yourself that every single integer falls into one of these sets. So if I take any given integer, it falls into one of these sets. And then whichever set it falls into, it will be congruent to all of the other numbers in that set. So for example, let's say we have an integer that is in this first green set. So for example, something like 195. Then I know that 195 is congruent to every single one of the other multiples of 5 in this green set. Now what would be the most convenient multiple of 5 to consider? Well, my favorite number from that set is 0. And so I'm going to label this set as square bracket 0. And that means that it contains all things that are congruent to 0. Out of the next set, the nicest number in that set is 1. And so on. In each of these, I'm going to choose to label them by a convenient representative that is a number between 0 and 4, because those are nice small numbers and they're much, much easier to work with. So now given some number like 107, I know it has to be in one of these sets because every number is. Which set is it in? Well, it's in that one right there. It's not too hard to see that. And so that means that 107 is really congruent to 2. So in the future, when I'm doing computation with 107 mod 5, I'll be able to just change 107 into 2. And that will be really convenient because I'll be able to write it as something much smaller. So that gets to the last thing that I want to do today is I want to talk about how to solve things of this form. Suppose I have x is congruent to a mod n, but I want a value of x that's between 0 and n minus 1. And so I'm just going to do several examples showing some different strategies for how to do this. The first strategy is to find the remainder. So the idea here, let's see, x is congruent to 22 mod 3. The idea is I'm going to divide 22 by 3 and see what the remainder is. So 3 goes into 22, 7 times. Remainder 1, that means that x equals 1. As another example, if x is congruent to 407 mod 11, I do 11 into 407 using long division. It turns out that it goes in evenly with no remainder, and so x equals 0. Okay, my second strategy is that I can take my number a and I can add or subtract any multiple of n until I get a value of x that's in the correct range. So as an example, let's consider x is congruent to negative 2 mod 7. I can add or subtract any multiple of 7. And the easiest one here is just to add 7 itself, and I get 5. 5 is in the correct range because it's between 0 and 6, and so that tells me that 5 is my answer. As another example, let's say x is congruent to 14 mod 4. I can add or subtract any multiple of 4, but I want to end up somewhere between 0 and 3, so I'm going to go ahead and subtract 12. When I subtract 12, I get 2. 12 is a multiple of 4, and 2 is in the correct range of values between 0 and 3, so that tells me that x equals 2. As another example, let's say x is congruent to 35 mod 6. So my first reaction to this might be that 35 sounds a lot like 36, and I know 36 is a multiple of 6, so I'll subtract 36. Unfortunately, that gets me a negative 1, which is not in the correct range, being between 0 and 5. But I can remedy that by adding 6 to that value, and I get 5. So x equals 5 is my answer. Perhaps if you were a little bit more on the ball than me, you might have realized that just subtracting 30 to start off would work, because 30 is also a multiple of 6. And if you did that, that's great. You have the right answer. One more example, x is congruent to 78 mod 9. So what multiple of 9 do you want to subtract from 78 in order to get an answer that's somewhere between 0 and 8? That's right. Excellent. You want to subtract 72. When you subtract 72, you get 6, so x equals 6. Okay, the last strategy is to count up or down from some multiple of n. So this strategy is kind of, I guess when I say I'm using this strategy, what I mean is that I'm picturing a number line. So x is congruent to negative 22 mod 4. So I want to picture a number line, and I want to find a multiple of 4 that's near negative 22. So in my case, I'm going to use negative 24. It's close to it. And then I count up or down from that multiple of 4 to the number I'm given. So here I can see that I have to go up 2 steps, and that tells me that x is 2. As another example, x is 292 mod 20. Well, a convenient multiple of 20 that's close is 300. So I'll start with 300. To get from 300 down to 292, I'm going to have to step backwards 8 steps back. So that means x is negative 8 mod 20. Now I'm going to combine that with the previous step, which was, or the previous strategy, which was I can add a multiple of 20. So I'll add 20 to that to get 12. Now I'm in the correct range, and so x equals 12. Okay, so I've already started a little bit using my last strategy, which is just combining the strategies I have so far. So 2 more examples. X is congruent to negative 313 mod 8. Well, if I wanted to use the long division strategy here, I might try that, but it wouldn't be clear to me what to do with the negative number. So what I'm going to do to start is I'm just going to ignore that negative number, and I'm just going to do long division, dividing 8 into 313. When I do that, it comes out to be remainder 1. Now, because I had negative 313, that means x is negative 1 mod 8. That's not in the correct range of being between 0 and 7, but I can use the other strategy of adding 8 to both sides of that to get 7. So x equals 7. As another example, let's say x is congruent to negative 947 mod 25. Well, I can use the strategy of adding or subtracting a multiple of 25 to make that number a little bit nicer. So I'm going to add 1,000. When I add 1,000, I get 53. Now I know that x is congruent to 53 mod 25, and then I can use long division to see that 25 goes into 53 with remainder 3. And so x is equal to 3. Okay, so all of these strategies that I'm using, first of all, if you think about them a little bit, I think you'll see that they're really all the same thing, just phrased slightly differently. But it's worthwhile, I think, to point it out and to point out each one and how to think about them, because some of them can be done mentally faster than others, and being able to use some agility in going back and forth between the different strategies can enable you to be able to reduce numbers mod n very quickly. Secondly, you're probably never going to see me at the chalkboard in class or on homework or on anything that would be handed in expecting this kind of work to be shown. So I've written it all out here so that you can follow what I'm doing mentally. But in practice, most people that employ these strategies just use them mentally and just pick the strategy that they can do most easily to find the answer that they're looking for. So hopefully with a little bit of practice, you too can be very quick at reducing numbers mod n. Okay, thanks, bye.